Welcome to AskPrep. My name is Uganavi. In today's class, we will study a new chapter of class 11 called Thermodynamics. So, what is basically thermodynamics? Thermo means heat. Dynamics means study of the process. So, it is a branch of science which deals with the quantitative relationship between heat and other forms of energies. It is called thermodynamics. So, for example, chemical energy, which is stored by molecules, is released as a heat during the chemical reactions. So, when a fuel like methane, cooking gas, or coal burns in air, this is also a thermodynamic process. The chemical energy, which is used to do the mechanical work when a fuel burns in an engine, and the chemical energy, which is used to provide electrical energy through galvanic cell, it is called the dry cell. So, the study of these energy transformations, which forms the subject matter of thermodynamics. And the laws of thermodynamics deals with the energy changes of the macroscopic system, which involve large number of molecules rather than microscopic system, which consists of a few molecules. So then what are the basic thermodynamic term? System. The system is a part of universe in which the observations are made or the system is under investigation. So the next term is surroundings. Surroundings is a part of universe other than the system. So the surroundings include everything other than the system. So we can see here this is the system, and around the system the surrounding is present. So we can see here. So universe is system plus surrounding. For example, so if we are studying the reaction between two substances A and B, which is kept in a beaker, so a beaker containing the reaction mixture is the system, and the room where the beaker is kept is the surrounding. So this system and surroundings are separated by a boundary. So this is the boundary, the separating system and the surroundings. And this boundary may be real or imaginary. So the next is types of system. Open system, closed system, and isolated system. So in open system, what happens? There is exchange of energy and matter between the system and the surroundings. So for example, the presence of reactants in an open beaker. So this is the example of an open system. Here the boundary is imaginary. So we don't know the boundary. There is no boundary between system and the surrounding. So the next is closed system. Here there is no exchange of matter, but exchange of energy is possible between the system and the surroundings. For example, the presence of reactants in a closed vessel which is made up of a conducting material. So the next is isolated system. So in isolated system, there is no exchange of energy and matter between the system and the surroundings. So the presence of reactant in a thermos flask or any insulated vessel. So the next is state of a system. The state of a thermodynamic system, which is described as the measurable or macroscopic properties. So the state of a gas is determined by pressure, volume, temperature, and amount. The variables like P, V, and T, these are called state variables or state function, as the values depend only on the state of the system or now how it is reached. So the macroscopic properties whose values depend only on the state and not on how the state is reached, this is called the state function. For example, P, PV, internal energy, enthalpy, and entropy. And the path functions depends on the path taken to reach from one state to another. So the next is adiabatic system. So the system which will not allow the exchange of heat between the system and surroundings within its boundary, but the energy of the system may change with the work. This is called the adiabatic system. The adiabatic process, it is a process in which there is no transfer of heat between the system and the surrounding. And the wall separating the system and the surroundings is called the adiabatic wall. This bursting of tire is an example of an adiabatic wall. So this reaction happens so fastly that there is no enough time to exchange the heat with the surroundings. So the next is internal energy. Total energy of the system is called internal energy. So whatever the energy may be. So it is the sum of kinetic, potential, chemical, electrical, mechanical, all the energies. So the internal energy is a state function and it depends on the initial and the final states of the system. Absolute value of internal energy which cannot be determined because we don't know at what state or what time the energy may move on or get up. So absolute value we can, approximate value we can give. So the change in the internal energy which is determined by delta U is equal to U2 minus U1, that is the final minus the initial state. So the internal energy changes when you supply heat into the system or when its work is done by the system or when the matter enters or leaves the system. So the next is changing internal energy base. Work. So considering an adiabatic system, the initial state of the system is A and its temperature is TA. So internal energy of the system in the state is A is equals to UA. So we can change the state of the system in two different ways. So one paddles. So the final state is P state and its temperature is TB. So if TB is greater than TA, so then the change in temperature is given as delta T is equal to TB minus TA. So the internal energy of the system state P is UP and the change in internal energy is delta U is equals to UB minus UA, that is work done by the adiabatic system. Therefore, internal energy U of the system is a state function. The work of the adiabatic system is positive when the work is done on the system and the internal energy increases. So if the work is done by the system, PAD is negative, that is work done by the adiabatic system, because internal energy decreases. So another way is, so if you take equal amount of the electrical work, when it is dipped in an immersion rod, you have to note down the temperature change. So we can find that as change in temperature increases, that is the change in internal energy is delta U is equal to UB minus UA, that is work done by the adiabatic system. So therefore internal energy U of the system is a state function. So J.P. Joule he showed that the amount of work done on the system, no matter how it is done, it produces the same change of state as measured by the change in the temperature of the system. So by convention, what happens? Work done on the system is equal to positive work, it is internal energy of the system increases. Work done by the system is negative, so internal energy decreases. So the next is heat. So if system and surroundings are at different temperature, internal energy of the system is changed by transfer of heat through thermally conducting walls. If temperature of the system TA and temperature of the surroundings TB, so TB is less than TA, so that is indicating heat is transferred from system to surroundings, so TB is equals to TA. So if TB is greater than TA, heat is transferred from surroundings to system till TB is equals to TA. So what happens in this case? The internal energy change, that is delta U, is equals to Q, because no work is done at constant volume. So by convention, if Q is positive, heat is transferred from the surroundings to the system and the internal energy of the system increases. So if Q is negative, heat is transferred from the system to the surrounding. So as a result, decrease in the internal energy. So the next is first law of thermodynamics. So it is stated as the law of conservation of energy, that is, energy can neither be created nor be destroyed. So delta U is equal to U2 minus U1, that is Q plus W. So this is the mathematical statement of first law of thermodynamics. So it is stated as the energy of an isolated system is constant, where Q and W are the path functions. And Q plus W is equals to delta U. So as it depends upon the initial and the final state of the system. So whereas it is independent of the way the change is carried out. So if there is no transfer of energy as heat or work as an isolated system, so W is equals to 0, Q is also 0, then delta U is also 0. Work, pressure, volume. So a cylinder contains 1 mole of an ideal gas which is fitted with a frictionless piston. So initial volume of the gas is Vi and the pressure of the gas inside is P. So pressure, external pressure is greater than the normal pressure, and the piston is moved inward till P external is equal to the normal pressure. So final volume is Vf. So what happens here? Piston moves at a distance L and its cross-sectional area of the piston is A. So if this is the piston, when it moves here. So what happens is from here there is an external piston of the piston. So this is Px is equal to delta V, that is a final volume to the initial volume. So when external pressure is applied. So what happens during this compression? Piston moves a distance L and its cross-section area of the piston is A. So then a volume change L into A is equals to delta V is equals to Pf minus Pi. So we know that pressure is equals to force by area. So therefore force on the piston is P external multiplied by A. So if the work done on the system is equal to the movement of the piston, then W is equals to force into distance, which is equals to Px into A into L. So Px is taken as the pressure external is minus of delta V. So minus of delta V is, so as there is the pressure volume of the final and the initial state, Vf minus Vi. So negative sign is used as an expression to obtain the sign for the work done. So that is why negative sign is used, so which will be positive. So what does it indicate? In case of compression, work done on the system, here Vf minus Vi will be negative and the negative multiplied by negative will be positive. So hence the work done is positive. So the next is reversible process. A process or a change is said to be reversible if a change is brought out in such a way that the process at any moment is reversed by an infinitesimal change or a very small change. So a reversible process proceeds infinitely slowly by a series of equilibrium states such that The system and the surroundings are always in near equilibrium with each other. So next is irreversible process. So processes other than the reversible process are known as the reversible process. So all natural processes are irreversible. So if the compression of gas is carried out in the number of finite steps, the work done on the gas will be sum overall the steps and will be equal to summation of P delta V. So this is the figure plotted of volume and pressure. So PV plot when pressure is not constant and it changes in finite steps during compression from initial volume Vi to final volume Vf, and the work done on the gas is represented by the shaded area. So the next is isothermal reversible process. So we have to consider a reversible expansion of ideal gas by volume dV. So therefore the isothermal process dE is equals to 0. Therefore dQ is minus dW. So the total work done during the expansion from V1 to V2, we have to integrate the differentiable equation as when we integrate we get work is P into delta V, PV. So V1 to V2. So P is nRT by V into delta V. So that is dV. So minus nRT ln V2 by V1. So W is equal to minus 2.303 nRT log V2 by V1. So as the temperature is constant, therefore P1 V1 is equal to P2 V2 or P2 by V1 is equal to P1 by P2. So the work done for the reversible system is written as the equation as minus 2.303 nRT log by P1 by P2. The expansion of gas in vacuum is called pre-expansion. So no work is done during the pre-expansion of an ideal gas, so whether the process is reversible or irreversible. So now we can write the equation in the number of ways, so depending on the type of the process. So now let us substitute W is equals to minus Px into delta V. So in the equation U is equals to Q plus W and we get delta U is equals to Q minus P external into V. So if the process is carried out at constant value, then delta U is equals to QV. The subscript V denotes that the heat is supplied at constant volume. So the next is enthalpy. So the heat absorbed at constant value is equal to change in the internal energy, that is delta U is equals to QV. So but many reactions are not carried out at constant volume but in flask or test tube under constant atmospheric pressure. So another thermodynamic function is the enthalpy. So the enthalpy is the heat content or warmthness of the reaction that is given by H is equals to U plus PV, that is internal energy, pressure and volume. So it is the sum of internal energy and the product of pressure and volume. So it is a state function and it depends on initial and final states of the system. And the absolute value of H cannot be determined. The change in enthalpy is determined, that is delta H is equal to H2 minus H1. So the next is mathematical statement of the first law of thermodynamics. So delta U is equal to Q plus W. So W is equals to minus P delta V. So at constant pressure what happens? Delta U is QP minus P delta V. So where QP is heat absorbed by the system and minus P delta V is expansion of the work done by the system. So let us consider two states 1 and state 2. The internal energy is U1, U2, volume is V1 and V2. The change in internal energy is U2 minus U1 is QP minus P of V2 minus V1. When you multiply, you get QP is equal to UT minus P delta V, PV2 minus U1 plus PV1. So from this we can H is equals to U plus PV. So H1 is equals to U1 plus PV1. H2 is equals to U2 plus PV2. So Q is the work done, H2 minus H1, you get delta H. So for finite changes at constant pressure, the equation H is equal to U plus PV, which is written as delta H is equal to delta U plus delta PV. As P is constant, we can write delta H is equal to delta U plus P delta V. So delta H is QP, which is the heat absorbed by the system at constant pressure. And delta H is negative for exothermic reaction, so which evolve heat during the reaction, and delta H is positive for endothermic reactions which absorbs heat from the surroundings. So at constant volume, delta V is 0, so delta U is QV. Delta H is equals to delta U plus P delta V. So delta H is QP is equal to delta U, which is QV, and the difference between delta H and delta U is not usually significant for systems consisting of only solids or liquids. And this solids and liquid do not any applicable for only significant volume changes upon heating. The relationship between delta H and delta U for the system having gases. So let us consider a reaction involving gases. So if VA is the total volume of the gaseous reactants and BB is the total volume of the gaseous products, Na is the number of moles of gaseous reactants and Nb is the number of moles of gaseous products. So at constant temperature and pressure, PVA is equal to NART and PVB is equals to NBRT. So PVB minus PVA is equal to NBRT minus NART. So when you group NB and NART as one, you get the NB or NG. So NG is the number of moles of gaseous products minus the number of moles of gaseous reactants. So P delta V is delta NG RT. So delta H is equals to delta U plus P delta V. So delta H is delta U plus delta NG RT. So the next is extensive and intensive properties. The extensive property is a property where value depends upon the quantity and size of the matter present in the system. For example, mass, volume, internal energy, enthalpy, heat capacity are the extensive properties. So those properties for which do not depend on the quantity or size of the matter, they are known as intensive properties. So for example, temperature, density, pressure, molar heat capacity are intensive properties. So if we consider a glass enclosed in a container of volume V and temperature T, so if we make that as partition of the volume is half, now it is V by 2, but the temperature remains the same. So it is indicated that volume is an extensive property, so temperature is an intensive property. So the heat capacity is the heat transfer to a system which appears as a rise in temperature of the system in case of heat which is absorbed by the system. And the increase of temperature is proportional to the heat transfer. So Q is equals to coefficient into delta T. And the magnitude of the coefficient depends upon the size, composition and nature of the system. So we can also write it as Q is equals to C delta T and the coefficient C is called the heat capacity. And we can also measure the heat supplied by monitoring the temperature rise So provided we know that the heat capacity and C is large, a given amount of heat which results only in the small temperature rise. And water also has a large heat capacity and a lot of energy is needed to raise the temperature. As C is directly proportional to the amount of substance, molar heat capacity of a substance, that is Cm, is equals to C by N, is the heat capacity for 1 mole of the substance, and the quantity of heat which is needed to raise the temperature of 1 mole by 1 degree Celsius. The specific heat is called the heat required to raise the temperature by 1 unit mass of a substance by 1 degree Celsius. So, for finding out the heat Q, which is required to raise the temperature of the sample. So, if you multiply the specific heat of the substance C by mass and temperature change delta T, as Q is equals to C multiplied by M multiplied by delta T, we get C delta T. So the relationship between Cp and Cv for an ideal gas. So at constant volume, the heat capacity C is denoted by Cv, and at constant pressure, it is denoted by Cp. So finding the relationship between two, we can write the equation for heat as Q at constant volume, Qv is equals to Cv delta T, which is equal to delta U. So at constant pressure, Qp, Cp delta T is equals to delta H. So the difference between Cp and Cv, which is derived for an ideal gas as, for a mole of an ideal gas, delta H is equals to delta U plus delta Pv. So that is delta U plus delta RT. So delta U is equals to R delta T. So delta H is delta U plus R delta T. So on putting the values of delta H and delta U, we have Cp delta V is equals to C delta T plus R delta T. So Cp is equals to Cv plus R, when you minus Cp minus Cv, which is equal to R. The measurement of delta U and delta H. So in calorimetry, what happens? It is an experimental technique which is used to measure the energy changes which is associated with the chemical or the physical process is called calorimetry. So calorimeter is a device which is used to measure the amount of heat change in a chemical or a physical process by measuring the temperature change. The measurements are made under two different conditions. So at constant volume Qv and at constant pressure Qp. The delta U measurement. So for chemical reaction, heat absorbed at constant volume is measured in a bomb calorimeter. Here what happens, a steel vessel is immersed in a water bath and the whole device is called calorimeter. And the steel vessel is immersed in water bath to ensure that no heat is lost to the surroundings. And a combustible substance is burnt in pure dioxygen supplied in the steel bomb. And the heat which is evolved during the reaction is transferred to the water around the bomb and its temperature is monitored. This is the bomb calorimeter. Since the bomb calorimeter is sealed, its volume do not change and the energy changes which is associated with the reaction are measured at constant volume. So under these conditions, no work is done as the reaction is carried out at a constant volume in the bomb calorimeter. And the temperature change in the calorimeter is produced by the completed reaction and then it is converted to Qv.